All right, so this is the review day 5 video. We're going to be working on review sheet 2. Your assignment for today is questions 10 through 15. We're going to do 11, 12, and 13 together. So we start out with optimization problems. With optimization problems, you have two equations. One of the equations you're trying to maximize or minimize. You sub the one equation into the equation you're trying to maximize or minimize, find the derivative, set it equals 0, and solve. So that's our general idea. So which points in the graph of this equation are closest to 0, 2? Well, if you're closest, you want to minimize the distance, so we're going to do our distance formula. So d is equal to the square root of x minus x1 squared plus y minus y1 squared. So we're going to fill in the 0 and the 2. So x minus 0 squared is just x squared plus y minus 2 squared. So this is what we're trying to minimize. So this is the equation we want to sub into. Our other equation in this one is just the equation of our graph. So we sub that in for y. And if we neaten that up, that parenthesis is really going to be 2 minus x squared, all squared. So if we FOIL that out, we'll end up getting 4 minus 4x squared plus x to the fourth. So d is really equal to, and I'm going to take that and combine it with the x squared that's already there. So we have x to the fourth plus, minus 3x squared plus 4. So when you're doing a distance formula optimization one, a technique is to go ahead and square both sides. That way we won't have to do chain rule over on the right, and we'll just do this as an implicit differentiation. So we're going to take the derivative with respect to x. So the derivative to d squared would be 2d times d prime. Now the reason this is going to work is the d prime is eventually going to be 0 anyway, so it's going to wipe all of that out on the left. And then this would be 4x cubed minus 6x. So again, the d prime will be 0, which will wipe out the whole left side. Over on the right, we can maybe pull out a 2x, leaving us with 2x squared minus 3. So if we set our 2x equal to 0, we just get x equals 0. And if we set this equal to 0, we would get x equals plus and minus square root of 3/2. When we add over the 3, divide by 2, and take the square root. Now, in an optimization problem, if you only get one answer that makes sense, you can assume that that is your correct answer, the maximum or the minimum, whatever you're looking for. So, because we didn't get one answer, we've got to do our number line. And again, you only have to do the number line if you're getting more than one answer that could possibly make sense. So we've got our minus square root of 3 over 2. We've got 0. We got positive square root of 3 over 2. So if we put a enormous negative, like negative 100 or so, into our derivative, we get a negative 20, and then the negative 10 here, or negative 100 times 2 is negative 200. The negative 100 squared is going to make this an enormous positive, so positive times the negative is a negative. if you put in, this is going to be bigger or further left of -1, because 3 over 2 is bigger than 1. So if you put -1 in, this is going to give us -2. This will give us -1 squared, which is 1, times 2 is 2, minus 3 is -1. -1 times -2 will give us a positive. If you put in the positive 1, we'll get the same negative here, but now a positive there, so you get a negative. And if you put in positive 100, you'll get positive and positive, so a plus. So we've got minimum, maximum, minimum. So the closest is happening at these 2 points, or those 2 x values, because remember, a parabola is symmetrical. So this is a parabola tipped upside down and shifted up 4. So that's why there's going to be 2 spots that are both the closest. So we got the x value of minus radical 3 over 2, positive radical 3 over 2. And our original equation was 4 minus x squared. From right here. And we'll just sub that in to get the y values. Because of the squared, we're going to get the same thing for both of them. So I'm just going to sub in the positive version. If we square the square root, we'll get 3 halves. So I'm going to rewrite 4 as 8 halves. 8 halves minus 3 halves is 5 halves. So we would just get 5 halves for our y value of each of these. And these are the points that would be closest to the point 0, 2 on our graph. All right, going on to question 12. Now you know a question is an optimization problem if it asks for the greatest or the least of something. So here we have a rectangular page. There's 24 inches of print. The margins of the top, bottom, left, and right are given there. What dimensions of the page should we have so that the least amount of paper is used? So let's draw a picture. So here's our rectangle, and then we've got the printed space in here. So let's call this x and this y, say. So one thing that we know is the printed space, xy, should equal 24. Actually, let's do this. I want to switch something. Because we eventually want the dimensions of the page, it might make more sense. Let's call the entire page x and y, because then we won't have to do anything extra at the end. So let's call that x and y. Well, they told us that top and bottom margins are 1.5, and left and right are 1. So we need to set up 2 equations. One, we want the least paper used. So that equation, we want the area of the paper. So area is equal to xy. And then the other, we need the printed area. So we have 24 is equal to, well, this horizontal length at the bottom is x with 1 chopped off on each side. So we would have x minus 2. And the vertical length of the printed area is y, but with the 1.5 chopped off on top and bottom. So that would be y minus 3. So we want to sub into the one that we're trying to minimize, so this right-hand equation, meaning we need to get x or y by itself over on the right. I'm going to go ahead and get y by itself. So we'll divide over the x minus 2. And then we'll add over the 3. And that's what we're going to sub in for y. So if we distribute our negative through, we get 24x over x minus 3 plus 3x. So we're now going to go ahead and take our derivative. So A prime is equal to, for the first term, we've got to do a quotient rule. So we've got low D high minus high D low all over low low. And then our derivative of the second part is just 3. So we're going to make the A prime be 0. When we do that, we can say subtract the 3 over. So we'll get minus 3 equals, if we distribute the 24 through, we get 24x minus 72 minus 24x over x minus 3 squared. Oops, I forgot the x here. Notice the 24x's wipe out. So we have negative 3 equals negative 72 over x minus 3 squared. We can put the negative 3 over 1 and cross multiply. And I'm just going to leave the negative 3 out front because we'll divide that over in a second. When we divide the negative 3 over, okay, something I knew didn't look right because this isn't going to eventually be a perfect square. I miswrote something. Some of you may have caught it. This was a minus 2 here. So we just got to carry that through. So that's x minus 2. So from our quotient rule now, that's x minus 2. Then this is x minus 2 squared. So when you distribute that through now, this is going to be a minus 48. And this is x minus 2 on the bottom. So just a couple small fixes. These are both minus 48. And then we should be back in good shape. Because now when you divide by negative 3, negative 48 divided by negative 3 gives us 16. Which is nice because when we take this square root, it'll work out nice. Set up two equations. And I didn't switch, hold on one second. I didn't switch the x minus 3 here. Sorry about that. So that's x minus 2, x minus 2, x minus 2, x minus 2, and x minus 2. Okay, so we have 4 equals x minus 2, negative 4 equals x minus 2. Add the 2 over in each case, we get x equals 6 and x equals negative 2. Well, x represented a length in our paper, which we can't have a negative, so we can reject it. So we don't have to do the number line because it's only one thing. And then we just need to find the y as well because they wanted the dimensions. Well, here was our equation for y. So we just found x was equal to 6. So if we fill that in now, this will give us 6 minus 2 is 4 in the denominator. 24 divided by 4 is 6. 6 plus 3 is 9. So y is just 9. And our units on each of those is inches. So we're 6 inches by 9 inches. All right, and the last one we're going to do on this video is number 13. So you have position, velocity, acceleration problems. Sometimes with these, you'll start with a constant acceleration of -32, because that's your acceleration of gravity in feet per second squared, and then you'll do antiderivatives. This one that we're going to do is a little different because they already give us the height equation. We want to know, when does the diver hit the water? Well, when you hit the water, the height should be 0. So for part A here, we'll put 0 in for the height. So we can start out, let's divide everything by a -16. So we got t squared minus t minus 2. So we got t minus 2 and t plus 1. So we'll get t equals 2 and t equals -1. Well, time can't be negative, so we'll reject that one. So we got at 2 seconds. Next, we want to know the diver's velocity at impact. Well, what we just found a second ago was the time of impact. If we know the time of impact, we can then find the velocity at impact by just subbing this time into the velocity function. Well, velocity is just the derivative of height. So we'll have -32t plus 16. We can find v of 2. That would give us -32 times 2 plus 16, which is -64 plus 16, or in other words, -48. And our units is feet per second. Now the reason it's negative is because the diver is heading downward when it is hitting the water. All right, so you've got the rest of questions 10 through 15 to finish up on review sheet 2.